Wonderful. We've seen how to quickly get a sniff of how our machine learning model's doing and evaluate it using the score method, and that'll return a default evaluation metric depending on the problem we're working on. In regression, it returns the coefficient of determination, and in classification, it returns the mean accuracy. However, when you get further into a problem, it's likely you'll want to start using some more powerful metrics to evaluate your model's performance. And so naturally, the next step up from using score is to use a custom scoring parameter. So if we see here, we've looked at this one, estimator score method, and now we're going to have a look at using a scoring parameter. Model evaluation tools using cross-validation. Oh, we might have to see what that is. So let's dive into it, hey? What we're going to do is to work this out. Now, you'll have to bear with me for the next few videos because we're going to cover a fair bit here. Reason being is because evaluating a machine learning model is such an important step. It's one thing to call a fit function on some data, but the next most important thing is going, hey, is that model actually working? Is it learning something? Could we use that to predict in the future? And so that's why I'm making sure that we're covering a lot of ground here. So let's get started. What we're going to do is go from Scikit-learn.model selection, import cross-val score. And as always, we're going to run the code first before we dive into what's actually going on. And what we do need is some classification code. So what we're going to do, we can copy this. You're allowed to copy this, by the way, because we've written it a fair few times now. So only thing different here of what we've done is we've imported cross-val score from Scikit-learn's model selection. Now, the next thing we're going to do, because we've called fit there, we'll just put a little semicolon so we don't get a big output. You know what? This warning keeps coming up, so we might just keep changing that to n estimators equals 100. Wonderful. And so, cross-val score. It has the word score in it, but we've seen, what is this cross-val doing? Well, let's have a look. So go co.score. We're going to do the test data first so we can compare. And then we'll do the same, but this time using cross-val score. Cross-val score. And cross-val score takes our classifier, it takes the X data, and it takes the Y data. Right? Not the test, and not the train. We'll see what's going on in a second. What's happening here? And again, we're getting another warning. This is just to say that the default value of CV will change from 3 to 5. So if we have a look at this, Shift Tab, let's read the docstring. Evaluating a score by cross-validation. What even is cross-validation? And so CV is going to give us a warning. This is where that warning is coming from. If we change this from CV equals, the default is 3. If we change it to 5, that warning is going to go away. And now we're going to get an array back of 5 different scores. So that's probably the first difference that you'll notice. Cross-val score returns an array, whereas score only returns a single number. Okay, so how can we figure this out? We need to figure out what cross-validation is, because that's, after all, what cross-val score is doing. Come back into the docstring, evaluate a score by cross-validation. Well, unlucky, here's something I prepared earlier to demonstrate, and as always, I understand things better visually, you might do the same, to demonstrate what cross-validation is doing. So, what we've done before in our normal train and test split, so we've split our data into training. So this could be, say we started off with 100 patient records. We'd split it into a training split. In our case, we've used 80%. And this would contain X train and Y train, 80 samples. And I've used the number 100 here. We've really got more than that, but this is just because the numbers work out visually better here. And in our test data set, we've got 20% of the data, which would contain X test and Y test. Now, the difference here with cross-validation, and in our case, this image here is demonstrating 5-fold cross-validation. What you'll probably see cross-validation referred to is K-fold, where K is an arbitrary number. And the reason why we're using 5 is because if we come back here, CV equals 5 there. So that stands for cross-validation. And this is what I'm talking about, splitting our data into training and test, using 20% for the test size. So that means naturally, the other 80% goes to the training data, which is where this little split here comes from. Now, what cross-validation does is it does 5 different splits. So it'll use the first 20%. So see how here this is kind of using the last tail 20% here? So it'll create a test data set here and a training data set here. Then it'll move over here and use this as the test data set. And then again and again and again. And so what happens is that cross-validation trains 5 different versions of the model. And then it evaluates those models trained on each training data on 5 different versions of the test data. So what's the purpose of this? Well, as you could imagine, if we're only training one model, it could be a lucky split. Like say this 80% of rows, say that had a whole bunch of information and the model was able to learn really well on these 80 rows, on these 80 patient records. And then it got a really good score on this test set. Is that a true reflection of how our model would understand the data or figure out the patterns in the data? Well, not really, right? Because it's just luck, right? If we're just splitting this randomly and somehow a bunch of easy patient records have gotten here and the model's figured out certain patterns and it's gone over to here to this test data set and it's got an amazing score, we could be tricking ourselves. We could be fooling ourselves into thinking that our model is far better than what it actually is. So that's where cross-validation comes into play. It aims to provide a solution to not training on all the data and avoiding getting those lucky scores on just a single split of data. So it'll create 5 different splits. So no matter what, our model is going to be training on all of the data and evaluated on all of the data. And so this is why if we come back to see cross-val score, it's why it gives us back 5 different scores here. So that's starting to make sense. So if we call the score parameter on only our X test data and our Y test data, it's going to give back 1 score. But if we call cross-val score, because we refer back to the graphic here, it's going to make 5 different splits. And remember, 5-fold is just an arbitrary number. You could do 10-fold, you could do 3-fold, you could even do 100-fold. But 5-fold is the default of the library, and it's usually pretty good depending on the size of your data. So we'll use 5-fold to demonstrate here. Just to prove it to you, we could go in here, cross-val score. We could even do 10. So this means it's just going to make 10 different splits, exactly the same as this, and then return 10 different scores. So you see here, this is a great example. On split 1, it's got a score of 0.9. So that could be 90%, which is higher here. But on a later split, it's got something much lower, 72. And so what we do here is to figure out a more ideal performance metric or evaluation metric for our model is that we can take the average of these 5 scores. Let's see it happen. We'll do it all in one cell. Random seed. And what we're going to do is get a single training and test split score. I'm going to make sure CLF single score equals CLF score X test. It's going to use the same data here. Y test. Wonderful. And then we're going to go take mean of 5-fold cross-validation score. CLF cross-val score equals NP mean. Then we need cross-val score. X, we need to pass it our classifier. X, Y, and we'll use CV equals 5. And then compare the two. So we'll go CLF single score and then CLF cross-val score. Boom. So, what do we see here? Well, in our case, our original single score, which is now down here, just the exact same number because we're using a random seed, using the same test data. Our single score is 0.85, but when we use cross-validation, when we use 5 splits, because CV equals 5, we get a score of 0.82. So it's slightly lower, but in this case, if you are asked to report the accuracy of your model, even though it is lower, you'd prefer the cross-validation metric over the non-cross-validation metric. Now wait, we haven't even used the scoring parameter at all. Well, that's because by default, it's set to none. Let's have a look. Scoring parameter set to none by default. So if we call cross-val score, CLF, X, Y, CV, we can pass scoring here, and it's going to be set to none. So if we do Shift Tab on this, how do I know this? Well, luckily the doc string comes in handy. See, by default, it's set to none. So if we keep scrolling down, move our notebook. So scoring, string, callable or none. Optional, default, none. Ah, okay. A string, C model evaluation documentation, that's what we've had a look up here. Or a scorer callable object / function with signature scorer estimator XY, which should return only a single value. If none, the estimator's default scorer, if available, is used. Ah, okay, now this is why we know that this is accuracy, because if the scoring parameter of cross-val score is none, it uses the default scoring parameter of our estimator. And in our case, what is it? Default scoring parameter of classifier equals mean accuracy. And where did we see that before? We saw that in the last video when we go clf.score and we hit Shift Tab. Returns the mean accuracy on the given test data and labels. So that means when we have scoring set to none, it's going to use the default evaluation metric for cross-validation on our classifier. So if we hit Shift and Enter, it's going to return the same values, or it might be slightly different, right? Because we haven't set up a seed in this cell. So these values are going to be different to the cross-val score we see up there. If we'd run it in here, we would have seen similar values. Whew, what have we covered here? Well, as you might have guessed, the scoring parameter can be changed, right? So we can, as the docstring says, we can input our own scoring parameter here. We can change this to something other than none. That is what we're going to start to cover, right? We're going to have a look at in the next few videos some other classification model evaluation metrics that we can use with cross-validation. And so why we use cross-validation? Well, as we saw in the picture, cross-validation aims to solve the problem of not training on all the data, right? So we're creating 5 models and we end up having a model trained on all of the data, and avoiding getting lucky scores, so training on a single split. And we saw that in action with our single split score here, getting a slightly higher score than our cross-validation score. Whew, that's a lot. Now, we've still got a bit more to go. Let's get some in-depth classification metrics happening. I'll see you in the next video.